Okay, we should be live. As you know, we are developing this website called BioniChaos.com. Go check it out right now. We have a bunch of new tools for you to test and explore. We have advanced hair cell simulation. This is hearing, to do with hearing, hearing simulation, auditory hair cells. So that to do with cochlea implants, neural firing, tonotopic mapping. Go check that one out. We have another one on a behavioral task, while doing like an emotional arousal, while listening to music, different types of music, while doing a cognitive test, so memory test, and at the same time it's a simulation where your respiration, ECG, cardio wave, and stress level are being recorded. We have an interactive TMS, transcranial magnetic stimulation simulator, for you to check out. It's a 3D visualization, highly interactive. And we have a game simulation for action potentials. We have different conditions, myelination, levels, ion channel densities, axon diameter. You can play with those, and there's also tasks for you to accomplish, to complete. So go check that out. Now, we had a question on LinkedIn, not on YouTube. Most of my traffic is actually coming from LinkedIn. That's okay. There was a question about the advanced EEG signal simulator. There was actually two questions, like who is it for, which, yeah, we'll just hand that over to the bots. But there was also another interesting question, is the fact that the artifact, when we adding artifact to the signal, actually have to make this, adjust the screen size to say 67%, so you can see both frequency and time domain. Yeah, so the question was, when adjusting, so say when doing eye blinks, wait a sec, no, let's do this one. So when doing eye blinks, it does not, you cannot currently set the timestamp for the artifact. So very good question. Someone actually went and checked the tool and asked a highly relevant question. Thank you very much for that. So currently we don't have that functionality. It's just mixing all the artifacts together. You can see how the artifact is affecting both the frequency and time domain. So when you're adding muscle, you can see a higher, so let's remove the eye blinks for a sec. So you can just see the difference. For the muscle EMG, you have this higher frequency addition being added to the spectrum. You can see it as that noise, higher frequency noise in the time domain as well. But no, there's no way currently. It could be a future version of this web application simulation synthetic signal EEG generator. We could add this later on, but currently it's not available. But you can see the overall result of adding EMG to the signal. And same for the eye blink. Those will be those low frequency components, and you can see them both, the frequency domain changing. You have this addition, you can play with it, see the difference, and you have those random eye blink artifacts in the time domain series as well. So yes, currently Unfortunately, well, we didn't want to make it too complicated. Already, this tool already doesn't fit the screen. It has quite a lot of stuff, so we didn't want to make it way more complicated. So we might add these things into future tools, those suggestions. And also we'll just have a notebook LM. We popped all this discussion, that's essentially what I just said. We popped it into notebook LM by Google, and it will, do the podcasty thing. Professional AI podcasters will essentially repeat what I just said. Hopefully it will make way more sense.
Or just, sit there and wonder what absolute electrical chaos is going on inside your head. Or maybe, more practically, how you'd even start making sense of it if you needed to.
Yeah, it seems like this overwhelming tangle, right? All those signals firing. How do you even begin?
Exactly. It feels almost impossible. But what if there was a way to, cheat? A shortcut to see the basic building blocks without getting totally lost in the noise.
Well, that's pretty much what we're diving into today. We're looking at EEG, electroencephalography, but through this specific lens of an advanced EEG signal simulator.
Okay, so our mission, if you will, is to demystify these brain waves a bit.
That's the plan. Understand why making a synthetic version is actually super useful, and uncover some, frankly, kind of ironic truths about how even simulated data gets messy. More interesting, maybe.
And we're basing this on two main sources.
The main documentation for the simulator itself, that's our blueprint. And then this other paper, ECG Signal Simulator, Design and Future Enhancements.
Wait, ECG, heart signals.
I know, right? Classic mix-up in the title. But it's actually full of user feedback and the designer's own thoughts on the EEG simulator. A bit of a lucky find, actually.
Okay, good. So, listener, whether you're deep in neuroscience or maybe an engineer or honestly just curious about how your own brain ticks, this should give you a more intuitive handle on things.
Yeah, spotting patterns, maybe even appreciating the beautiful chaos of it all.
Right. Okay, let's just cut to what is EEG. We hear the acronym. What's actually being measured?
So electroencephalography, EEG, it's non-invasive, which is key. It basically records the electrical chatter of your brain from the scalp.
It's not like sticking probes in.
No, definitely not. These brain waves are single neurons firing off alone. Think of it more like a combined hum, synchronized activity from huge groups of neurons working together.
Okay. Listening to the roar of a crowd and one person shouting.
Exactly. And analyzing these gives us really valuable insight. Cognitive states, neurological issues, just general brain function, like listening to the brain internal monologue.
Yeah.
Sometimes it's quiet, sometimes it's, well, noisy.
So, if we can get this data from real brains, even if it's messy, why bother making a synthetic version? Isn't that, I don't know, like studying a classic model of the brain instead of the real deal? Where's the edge in faking it?
That's the interesting part, isn't it? The fake one has superpowers, the real one doesn't. A synthetic EEG signal is artificial, yeah. It's designed to perfectly mimic the characteristics of real brain activity.
Okay.
And its biggest strength, it's totally controllable, predictable. You can dial in the specific fundamental brain waves, delta, alpha, and quickly, you can deliberately add the noise, the artifacts that drive researchers crazy in real data. But you add them precisely.
What do those different waves, delta, etc., actually represent again? Just
Sure. So delta waves, it's typically sleep, very slow wave. Theta often shows up in drowsiness, light sleep, or deep meditation, kind of floaty state.
Right.
Alpha is your classic relaxed wakefulness. When you close your eyes, just chill for a second. Big indicator there. Beta waves, that's your active, thinking, problem-solving, alert brain, your everyday on state, basically. The simulator mix these together however you want.
gotcha. So it's like having a controlled experiment set for brain signals. You can isolate things. That sounds incredibly useful, especially if you're trying to learn this.
Really, for education, it's a huge shortcut. Students, researchers, they can instantly see how, say, adding more alpha changes the waveform, or what a blue artifact looks like in the both from the raw signal over time and the frequency breakdown, the power spectrum.
Instead of just reading about it in a book.
Exactly. It builds that intuition super fast. And for developing algorithms, It's total godsend.
That's-
Well, if you're building code to remove noise or detect certain brain states for a brain-computer interface, you need to test it. Using the simulator, you test it against the signal where you know exactly what's in it. A perfect ground truth.
So if you're messed up, you can't just blame the messy real-world data.
Precisely. The input was clean, or at least controlled in its messiness. It takes away a huge variable when you're debugging. It just simplifies that chaotic, real EEG look.
So you can actually see how the different parts add up to the final signal you observe, like getting the recipe and the ingredients list.
That's a great way to put it. It helps you build that intuition piece by piece.
Okay, so who is this actually built for? Is it just for hardcore neuroscientists and signal processing engineers? Or is it broader?
Well, the sources are pretty clear on this. The designer aimed for a broad audience. Yes, neuroscientists, yes, engineers working on but also students, researchers, data scientists.
So basically anyone interested in getting a feel for how these electrical components mix together.
Exactly. Anyone who wants to build that intuition for what makes up an EEG signal. It's meant to be accessible, but still powerful.
Okay, let's get hands-on, conceptually at least. The docs describe it as interactive, right? Controls on one side, visualizations popping up on the other.
Yeah, you tweak something, you immediately see the result. Instant feedback. It's great for learning. Or, instantly seeing how badly you just messed up your simulated brain.
The controls. Sounds like where the fun starts, like a DJ mixer, but for brainwaves?
Pretty much. You've got these brain state presets, quick ways to load common states, click relaxed meditative.
And boom, lots of alpha waves show up on the graph.
Exactly. You see that characteristic peak in the power spectrum. It makes the textbook descriptions suddenly click. You see it.
But then there's the artifact simulation. This is where you get to inject the chaos deliberately, right? The stuff that ruins real experiments.
Yeah, the non-brain electrical signals. The simulator lets you play with two big ones. First, muscle artifact, EMG. That high-frequency fuzz you get when someone tenses their jaw or neck.
Oh, yeah. Noise.
Total noise.
Mm.
It can completely swamp the brain signals you're trying to see. The simulator lets you dial that frustration right in.
And the other one?
The infamous EOG, eye blink artifact. These huge, slow voltage spikes that happen every time someone blinks. They look like massive mountains on the EEG trace.
So your subject is trying to concentrate, but their blinking just obliterates the subtle brainwave you're after. It's almost funny how disruptive basic biology can be.
It really is a kind of dark comedy in neuroscience sometimes.
Yeah.
But here, you control the chaos. You decide how much muscle noise, how frequent the blinks, and beyond those, you have the fine-tuned waves controls.
This is for getting really specific.
Yep. Simple sliders let you adjust the overall power, like the volume of delta, theta, alpha, beta. Quick and easy. But then there's a customized mode.
For the control freaks among us.
Exactly. Here you can set the precise center frequency for each wave band, the bandwidth, how wide that frequency range is, and the amplitude, the strength. Total granular control to craft your signal.
And how do you make sense of the signal you've just crafted? There are overlays.
Right, the spectrum overlays. These are dotted lines showing the theoretical perfect shape of each individual brainwave band you set up. They act as a guide.
So you can compare your ideal ingredient shape to what actually comes out in the final mix.
Precisely, which leads us nicely to the visualizations on the right.
Okay, so you've mixed your brainwave cocktail. What does it look like? First up, the power spectrum, frequency domain.
This graph is the output of a calculation called a fast Fourier transform, an FFT. It breaks down your complex signal and shows how much power or energy is present at each frequency.
So you see peaks where your main brainwaves are, like a big peak in the alpha range if you selected the relaxed preset.
Exactly. It's the frequency composition view, essential for understanding what ingredients are strongest in your signal mix.
And below that, the simulated EEG waveform, time domain.
That's the raw signal. The moment-to-moment voltage fluctuation over time, usually shown over a few seconds. It's the sum total of everything you put in, all the brainwaves, all the artifacts, all interfering with each other. One single squiggly line representing that final cocktail.
Okay, so here's where it gets maybe a little weird or insightful. You've set everything up carefully, you expect clean results, maybe some controlled noise, but you look at that power spectrum, the actual blue filled-in area, and it doesn't perfectly match those nice, neat, dotted overlay lines for your individual waves. It's lumpier, messier. What's going on? Is the simulator broken?
No, not broken. This is actually one of the most fascinating and subtly brilliant parts of the tool. It's demonstrating a core principle of signal processing. That blue area is the final cocktail, as the source calls it. It's what happens when you actually mix all those waves together.
And the dotted lines are just the idealized ingredients before mixing?
Exactly. They're theoretical. When you mix real waves, even perfectly generated synthetic ones, they interfere with each other. Constructive interference, where peaks align and add up. Destructive interference, where peaks and troughs meet and cancel out, partially or fully.
So even in this perfectly controlled digital world, the act of combining signals introduces inherent complexity and messiness.
Precisely. It's unavoidable. The signals interact across all frequencies. That's why the final spectrum looks more complex, more lumpy than any of the individual smooth overlays. The overlays guide your eye, but the blue spectrum is the reality of the mixture.
Wow, that's quite ironic. A tool designed for clarity ends up demonstrating that even synthetic reality is inherently complex due to interference. No wonder real brain data is such a challenge.
It's a fantastic teaching point, really. It shows that the clean separation we might imagine just doesn't happen when signals combine. It's a no-fluff look at signal interaction.
It really drives home that point. Okay, let's shift from that kind of beautiful complexity to more practical matters. A user had a really sharp question for the designer, apparently, about the artifacts.
Yeah, this was insightful. They asked if you could see time-stamped markers for when, say, a muscle twitch or an eye blink artifact actually occurs within the raw time domain waveform.
Like a little flag saying, blink happened now.
Exactly. Pinpointing the exact moment. Because just knowing you set a 1 Hz blink rate doesn't tell you exactly where those blinks fall in the 5-second window you're looking at.
And what was the answer? Can you see those markers?
Currently, no. The designer explained that the artifacts are mathematically mixed into the final signal waveform. They aren't separate tracks with distinct event markers you can toggle on or off. You set the parameters, so you know they're in there contributing to the overall shape, but you can't isolate the exact moment of their occurrence visually with a marker.
I can see why that would be useful, especially for testing algorithms that are supposed to detect those events.
Absolutely. It's a key piece of feedback, and the designer acknowledged that, calling it a fantastic suggestion for a future update.
That's good to hear. Shows they're listening.
Definitely. It highlights how these tools evolve based on user needs. Adding timestamp artifact markers would be huge for teaching and validation.
So speaking of the future, what else is potentially on the roadmap for this simulator? It sounds powerful, but where could it go next?
Well, the designer has a few ideas based on the feedback in the field. One is incorporating more waveforms, like gamma waves, those higher frequency ones, above 30 Hz, linked to complex processing, maybe even consciousness itself.
Ooh, okay. Getting into the really complex stuff.
And other, maybe less common, brain rhythms too. Plus, adding more artifact types.
Like what? We already have muscles and eyes. What else messes things up?
Well, there's EKG interference, the electrical signal from the heartbeat bleeding into the EEG. That's a common one. And the classic 60 Hz or 50 Hz power line noise, that pervasive hum from electrical wiring that plagues sensitive recordings.
Oh, right. The bane of every lab.
Exactly. Then, getting into more advanced analysis, maybe adding spectrograms.
What would that show?
Spectrograms give you the time frequency view. So instead of just seeing the overall power at each frequency, like the current spectrum, you'd see how the power at different frequencies changes over time, like watching the musical score unfold.
That sounds incredibly useful for seeing dynamic changes.
It would be. And thinking bigger picture, multi-channel simulation. Right now, it simulates a single EEG channel. Simulating multiple channels would let users explore things like brain connectivity, how different areas might be communicating.
Wow, okay. That's getting much closer to simulating a whole brain network.
It's a big step, yeah. And finally, maybe allowing users to import their own real EEG data to compare it side by side with the simulated signals. That would really bridge the gap between the clean simulation and the messy real world.
Okay, quite a journey we took there. We've sort of peeled back the layers on EEG, seen why synthetic signals are actually brilliant for learning and building things in a controlled way.
And then we hit that twist, how even the controlled simulation reveals the inherent beautiful chaos of signal interference, that cocktail effect.
Right. This tool really seems to cut through the complexity by letting you build it up yourself piece by piece and see how it all interacts, messiness included. It feels very direct, no fluff.
And that kind of foundational understanding is just critical if you're working in neuroscience, biosignal processing, BCI development, or honestly, if you just want that deeper intuition about the brain's electrical language. It's a faster path to getting it.
So we end on this thought. We saw how even a perfectly designed, ideal simulated brain signal becomes this complex, lumpy, interacting thing once you actually combine its parts. It really makes you think, doesn't it?
How so?
Well, if even the most controlled synthetic version of brain activity is inherently subject to this kind of messy interference,
Hmm.
what does that imply about the perfectly clear, ideal thoughts or insights we sometimes imagine we're having?
Ah. Are they maybe just as composite, just as much a result of complex interference patterns once they manifest in our actual neural networks?
Exactly. Maybe that striving for pristine, perfect clarity is missing the point. Maybe the real understanding, the real richness, comes from embracing the beautiful interference. Food for thought.
Yeah, there is a human in the loop. If you have any questions, specifically after checking the website, of course. I didn't mean like questions about the meaning of life or why this YouTube channel exists. Let's do if there's no questions, let's do a quick musical break. So we're using Music FX DJ. Let's test this one. Okay, that's a bit annoying. Yeah, it's doing some random, giving you random stuff, and let's actually move on. We'll do music later again. Try it again. There's no questions in the chat, no. Okay, we finished this one. Could actually, yeah, so we'll jump onto something else, e.g. interpretation, the impact of signal processing, filtering, and any standards for filtering or lack of standards. Hopefully this will be, yeah, so this is specific to EEG, perhaps even EEG and epilepsy, but we will see how we go. Worst case, we update the podcast later on. And yes, obviously it's relevant to this tool that you see on the screen as well. And go check it out. There's a link. Should be a link in the chat.
Okay, let's unpack this. Imagine a doctor looking at your brain scan, right? Trying to figure out what's going on inside your head. A life-altering diagnosis hangs in the balance. Decisions about treatment, maybe even really difficult family conversations. Now imagine if that diagnosis could dramatically change. Not because your brain changed, but because someone just adjusted a setting on the machine. Sound wild, maybe a bit unsettling. Well, you're about to dive deep into the fascinating and frankly kind of ironic world of EEG interpretation. We're exploring where technology and medicine meet and where, the hard math bumps up against human expertise.
It is fascinating, and what's really striking here is how profoundly simple engineering choices made maybe years ago when designing the machine,
Mhm.
how they can impact really complex clinical interpretation down the line. We're talking about brain waves, the actual electrical whispers of thought being shaped, sometimes completely reshaped, by digital filters before a doctor even sees them. It's a critical step, but one that's, well, often overlooked, and yeah, definitely ripe with a bit of dark irony.
So let's zero in on this. The core of the problem, according to our sources, in electroencephalography, EEG, the specific settings used to process the brain's electrical signals can just drastically alter how they look on the screen. And we're not talking subtle changes here, are we?
No, not at all.
We're talking about the exact same underlying brain activity showing up as two completely different clinical patterns. It's almost like, I don't know, trying to diagnose someone's health from a photo that's been put through a bunch of weird random Instagram filters.
That's a pretty good analogy, actually. And the prime culprit, the main filter involved here that our sources point to, is often the low-frequency filter, the LFF, sometimes called a high-pass filter. Same thing, really.
Okay, the LFF.
Yeah. So take a pattern clinicians look for called burst suppression.
Right.
This is a really serious sign. Often means severe brain injury, deep coma. It's a critical finding. It leads to huge decisions, withdrawal of care, even brain death declarations sometimes.
Okay, so the stakes couldn't be higher. What happens with this LFF filter then?
Well, this is where it gets kind of shocking. The research clearly shows that by simply adjusting that low-frequency filter setting, maybe turning a virtual dial, that exact same piece of raw EEG data can be made to look like continuous slow-wave activity.
Which sounds less bad.
Much less bad. It suggests a far less severe condition. Different prognosis, totally different treatment plan, potentially. The irony is just profound. A tiny software tweak could, theoretically, shift a patient's diagnosis from severe, maybe even terminal, to something milder. Or the other way around, all without their actual brain activity changing one bit. It really makes you ask, how reliable is the interpretation when the truth on the screen can be manipulated almost by a setting?
So what does this mean for you, the listener? If you or someone you know needs an EEG, it means the consistency, the accuracy can vary a lot between hospitals, maybe even between different machines in the same hospital. You might literally get a different picture of your brain depending on the equipment or just the settings used that day. Feels a bit like getting your taxes done by accountants using different calculators with hidden quirks.
Right. And standardizing those filters, like maybe everyone agrees to use a 1 Hz LFF, as some sources suggest. That seems like a good step.
It's a crucial step, definitely.
But our sources say it's only part of the story, right? It's not just one knob.
Exactly. It's not just the LFF. That's maybe the most dramatic example, but the entire signal chain matters. From the tiny electrical pulse leaving a neuron in the brain, all the way to the squiggly line on the monitor, every single component can influence that final waveform. It's like a whole cascade of potential little distortions.
Okay, so break that down. What else is in this chain? Well, it starts right at the patient, with the hardware. The electrodes themselves, what they're made of, their size, shape, that matters. Then the cables carrying the signal, the preamplifiers that boost that tiny brain signal, because it is tiny. And then the analog to digital converters. That's the bit that turns the brain's smooth, continuous electrical waves into numbers a computer can understand. Each of these physical parts has properties that affect the signal quality, introduces noise, even before any software filtering happens. Think of it like recording music, the mics, the cables, the audio interface. They all color the sound before you even touch an EQ.
Okay, so the physical stuff matters.
Yeah.
Then comes the software part, beyond just that LFF setting.
Right. Then you get to the software and the algorithms. It's not just what frequency you cut off, like with the LFF. It's also about the type of filter. Is it a Butterworth filter? A Chebyshev. They sound technical, but they work slightly differently mathematically. And the filter's order, or steepness, basically how aggressively it cuts off frequencies. Different EEG software packages might implement the same setting, say LFF 1 Hz, in subtly different ways.
Huh. So even if two places use the same setting.
It might not be exactly the same, leading to slightly different waveforms, like different photo apps applying the sharpen effect. The name is the same, the result isn't quite identical. A steeper filter might cut noise better, sure, but maybe it also cuts off a subtle, slow brainwave that was actually important diagnostically.
And I guess we can't forget the patient themselves and just the real world messing things up.
Oh, absolutely. You always have what we call artifacts, noise that isn't brain activity. Things like the patient clenching their jaw, tiny muscle twitches in the scalp, even just sweat changing the electrical contact. Or interference from other electrical equipment in the room. You know, the hum from the lights, a nearby monitor. All that baseline noise is there before any digital filtering. And it makes the job of sorting the real brain signal from the junk much harder for both the machine and the doctor. It really demands you understand the whole process.
So the dream solution seems obvious. Standardize everything, every machine, every setting, everywhere, perfect consistency, a global EEG standard. But reading between the lines in our sources, that sounds, well, really hard, maybe impossible.
Yeah, perfect global standardization.
Yeah.
It's probably an unattainable ideal. Think about the costs, the legacy equipment out there, different manufacturers.
Right, it's messy.
Very messy. So the more realistic path, the one the sources really push for, is about transparency and education. It boils down to a few key things. One, clinicians absolutely need to report the specific recording and processing settings they use. Like, show your work, every time.
Put it in the report.
Exactly.
Okay.
Two, clinicians need to really understand how these filters and processing steps work, get fluent in the basics of signal processing. And three, always, always critically consider the source. Ask, what machine was this? What settings were used? How might that skew what I'm seeing right now?
So it's less about forcing uniformity, which might be a losing battle anyway, and more about smart interpretation, acknowledging the variables.
Precisely. It's about empowering the clinical expert, giving them the tools and knowledge to account for the technical side. That's the practical mitigation strategy. Make the interpretation more reliable, even if the raw inputs aren't perfectly identical everywhere.
Which brings us to this kind of funny, or maybe darkly funny, clash. The cold, hard math of engineering versus the, seasoned interpretive eye of the clinician. Our sources quote this viewpoint. Filter design is engineering and math. Clinical neurophysiology is mainly expert opinion engineering, and opinion don't mix well. Sounds like two different worlds, almost in opposition. The precise engineer versus the intuitive doctor.
It does sound like that. It's a common way to frame it, but it's fundamentally flawed. I think it's not a conflict. It has to be a partnership. They are totally codependent. The EEG machine is the engineered tool. It captures the data. The clinical expert is the skilled user who interprets that data, makes the diagnosis. Think of a Formula One car and the driver. One's an engineering marvel, the other has incredible skill and intuition. You absolutely need both. They're useless apart.
Okay, so they need each other.
Yeah.
Why the friction then? Why this feeling that they don't mix well?
Well, the friction comes from a lack of mutual understanding, usually. An engineer might design a filter that's mathematically perfect for removing noise, let's say. But in doing so, they might accidentally erase some subtle squiggle that a clinician with years of experience knows is a critical diagnostic clue. And conversely, the clinician who doesn't understand their filter settings, they might see an artifact, just a glitch from the machine or the processing, and mistake it for something real, something wrong with the patient's brain. That's where expert opinion can become unreliable, not because opinion itself is bad, but because it's disconnected from how the evidence, the waveform, was actually created by the tool.
So the expert's eye can be fooled if they don't understand the camera, essentially. That's quite the paradox.
It is, and the solution is just smarter integration. Standardization in this context isn't about dumbing things down. It's about using engineering principles to make that expert opinion more reliable, more consistent, more powerful. The clinician needs to know exactly what they're looking at, including the distortions the tool itself might have introduced. It's about technical literacy empowering expertise, knowing the map and the map maker's choices.
So wrapping this up, what's the big takeaway today? For me, it's that sometimes the deepest medical truths aren't just hidden in our biology, but also, kind of ironically, tucked away in the technical settings of the machines we use. It's a real reminder that even in something as critical as looking at the brain, a seemingly small technical choice can have these huge, maybe overlooked consequences. A real dance between the human expert and the machine.
Absolutely. And maybe it leave a question for you, the listener, to ponder, even beyond EEGs. In this age where we're flooded with data, with algorithms, with information presented to us, how often are we interpreting things, news, social media, whatever, without fully understanding the filters, the processes, the signal chain that shaped it before it got to us? What crucial details, what context might we be missing or misinterpreting simply because we don't fully grasp how the information was produced and delivered?
Definitely something to chew on, isn't it? Until our next deep dive, keep questioning your filters, both the literal ones and the metaphorical ones.
Yeah, there's a human in the loop if you have any questions. obviously, after checking the website, go for it. Yeah, this is the website we're developing, BioniChaos.com. Everything we do is available on the site. Go check it out.
We're making powerful biomedical tools accessible to everyone.
Ever wondered what your brainwaves sound like? Or look like? Ever wanted to play with real scientific tools? Ours are free and open source. You won't believe what you can do with your own data.
Want to dive into data science? Start with our interactive tools.
Go ahead. Play with the data.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Ever wish you could just, like, design a brain, not just daydream about it, but actually dial up a specific brain state? You know, super focused or maybe totally relaxed. Well, today we're sort of peeling back the scalp, metaphorically speaking, to look at a technology that lets you do pretty much that. And as we'll find out, it's way more profound and actually, funnily enough, far messier than just some kind of mad science experiment. So our mission for this deep dive, it's pretty clear. We're exploring the world of EEG, that's electroencephalography. And specifically, this really clever bit of tech that creates synthetic brain signals, fake ones. We'll get into why anyone would even want to generate artificial brainwaves, what makes them surprisingly real, and what they tell us about the super complex and, yeah, often very messy signals our actual brains pump out. We're given the fluff, jump right in.
Yeah, and what's really fascinating here is how these digital copies actually help us figure out the real thing. It's like building this controlled, almost sterile environment so we can understand what's usually just a chaotic mess of electrical noise in the brain. We'll look at how this helps researchers, helps developers too, and how it even helps us understand those ghosts in the machine, the annoying interference that messes up real recordings.
Okay, right, let's unpack that. So EEG, at its most basic, what actually is it? For anyone maybe not swimming in neuroscience daily, it's a way, a non-invasive way, to record the electrical chatter from big groups of neurons firing together. Brainwaves, basically. And these signals, they give us these incredibly valuable real-time insights into everything from like how focused you are to spotting neurological issues. But here's where it gets really interesting, almost like conducting a digital orchestra.
Exactly. So the thing we're focusing on today is the Advanced EEG Signal Simulator. It's a web-based tool, and it's specifically designed to generate synthetic EEG signals. Think of it like a really carefully crafted artificial waveform. It's designed to perfectly mimic real brain activity. It combines those fundamental brain waves we know, the slow delta waves of deep sleep, theta for drowsiness or meditation, alpha for relaxed wakefulness, and the faster beta waves for when you're alert and thinking hard. And, this is key, it lets you deliberately add in common sources of noise, what we call artifacts.
Ah, so it's like this digital sandbox where you're the puppet master dialing up focused or dreaming just by clicking around. That sounds, well, incredibly powerful.
It really is. You can literally fiddle with controls and watch the waveforms change right there on the screen. Imagine teaching, right? Instead of just static pictures, you could select, say, relaxed meditative from a menu, and boom, you instantly see this strong alpha waves pattern appear, just like you'd expect. Or you could tweak individual wave settings, like amplitude or bandwidth, showing exactly how tiny changes affect the whole picture.
Okay, but why? Why would you need a fake brain signal when you've got a perfectly good, if messy one, running in your head right now? It feels a bit counterintuitive, doesn't it? like building a simulation of a car to test how a real road works.
Yeah, that's a really important question. Why synthetic? And the answer, it covers a few critical areas. First, learning and education, it's just invaluable. Students can get an intuitive feel for how different brain states look, how waves combine. And they can do it without needing all the complex, expensive, often kind of finicky, real EEG gear. But maybe even more importantly, it's vital for algorithm development. Think about engineers, data scientists building tools for, say, brain-computer interfaces, or maybe new ways to spot signs of epilepsy. They need a reliable, predictable signal to test their code against real EEG. It's all over the place. So the simulator simplifies things. It gives them a clean baseline, helps them build and test their tools, especially the ones meant to remove those artifacts we mentioned.
Right, artifacts. Speaking of chaos, real brain recordings are never as clean as those perfect sine waves you see in textbooks, are they? They're always contaminated by these artifacts. It really is like trying to hear a whisper during a rock concert or, understanding someone across a really noisy bar. What are these things, these noisy gate crashers?
Well, in the real world, outside the lab, EEG recordings are just constantly getting contaminated by electrical signals that aren't from the brain. They come from your own body, but not your brain cells firing. And the simulator is smart because it lets you add in two of the biggest culprits. First, there's muscle artifacts, EMG. That's high-frequency noise from simple things like clenching your jaw or frowning, maybe even just tensing your neck muscles. And then you've got eye blink artifacts, EOG. These show up as these big, slow-wave spikes when you blink. Pretty obvious one, that.
So, wait, your own body is basically sabotaging the readings of your brain.
Mm-hmm.
That's actually darkly funny, isn't it?
Yeah.
The ultimate kind of self-inflicted wound in science. I remember reading somewhere that eye blinks are often called the most dominant unwanted signal in EEG. And they can actually mess with your theta and alpha rhythms, especially right at the front of the brain where lots of thinking happens.
Oh, absolutely. It's a huge problem. Imagine you're trying to get a clear read on someone's cognitive state, but every single blink throws this massive electrical spike that just obscures everything. It's a real challenge. And yeah, another study highlighted how big a deal muscle artifacts are, especially during sleep studies. They found it can make up like 20 to even 70% of the total signal power in those higher frequency ranges, say 15 to 32 hertz. So being able to spot and filter out these transient non-brain signals is just critical if you want to interpret the actual brain activity correctly.
Okay, so this is where the irony kicks in, right? We developed these amazing tools to create perfect synthetic brain signals, clean, predictable. But then reality is so messy that we actually have to make our fake signals messy as well, just so they're useful. That's just a brilliant, almost tragicomic twist in how science works.
It is, isn't it? A fascinating paradox. And the YouTube deep dive on this specific simulator points out something really important about that. The underlying Python code. It actually generates a random frequency within the specified range for each brainwave band every time you run it. So even if you use the exact same settings twice, the output signal will be slightly different. Now, this isn't a mistake. It's deliberate. This random variability makes the synthetic data much more like the natural, subtle fluctuations you always see in real EEG. Because think about it. If your fancy new algorithm only works on perfectly clean, unchanging waves...
It's going to fall apart the second it sees real data.
Exactly. It just won't survive contact with a real, messy, beautifully complex human brain signal. It needs to be stress tested on something closer to that reality.
Okay, this leads us to a really fundamental point then. If real brain data is just naturally full of noise and randomness from our own muscles blinking to the basic physics of the signal itself, how do we even know what's real brain activity versus just, background static? What does this mean for how we've traditionally looked at brainwaves? For decades even.
This is probably one of the biggest shifts happening in how we understand EEG right now. The main challenge is that the power spectrum of an EEG signal, how much power there is at different frequencies, typically has this 1F-like decay. What that means is you generally have lower power at higher frequencies. Think of it like a constant underlying hum or broadband noise that's just always there, kind of like static between radio stations. And the sources we looked at, especially that Sapien Labs paper, they show that the field historically has basically confused this background noise with genuine, distinct brain oscillations. Early researchers, they didn't have the computers we have now. They had to simplify. So they just started dividing the whole spectrum into these broad bands, like alpha waves here, beta waves there, and they kind of assumed everything within that band was one specific pure wave.
Whoa. So we've been calling these broad chunks of activity waves like the alpha wave for relaxation, beta for focus, but a lot of that might actually just be this background hum, This non-periodic noise,
Hmm?
that feels like a huge misunderstanding that's been hiding in plain sight. A fundamental assumption that might be, well, wrong. Does that mean, like, countless studies might need a second look?
It's a pretty profound realization, yeah.
Yeah.
The Sapien Labs paper really drives this home. It argues that traditional measures, like just measuring the total alpha power in that band, are often reflecting changes in that overall 1F background hum more than changes in a specific emergent rhythmic component. So what does that mean? It means a reported change in alpha power could just be because that background noise level shifted slightly. It might have nothing to do with a true change in actual brain oscillations.
Yeah.
And that has massive implications for how we've interpreted everything from brain states and cognition to neurological disorders. It definitely suggests that a lot of past findings might be looking at, well, maybe not the wrong thing, but misinterpreting where the signal change is coming from.
Okay, so if the old way is potentially flawed, how do we find the real signal, the actual rhythmic activity hidden in all that background noise? It sounds like we need a much smarter way to listen, something that can tune out the static.
We absolutely do. And that Sapien Labs paper proposes exactly that. A new metric they call oscillation energy, or E0, sometimes written E specifically for the alpha band. It's designed specifically to separate the true oscillatory peaks, the actual waves, from that pervasive, non-periodic background noise. Now, the method is a bit technical, involves things like autocorrelation, FFT, a second-order differential. But without getting lost in the math, think of it like a really sophisticated filter. It's designed to amplify the detection of those small, genuine oscillatory signals, making them pop out from the background hum. The beauty of it is that it's much less sensitive to those overall shifts in the 1F background noise. It's like turning down the static on the radio so you can hear the actual music underneath more clearly.
Now, that is fascinating. They tested this, right? What did they find when they compared EOR to the old alpha power measures? Because the classic finding is alpha goes up when you close your eyes. That's like EEG 101.
Exactly, and that's what they checked. They found that EA consistently, reliably increased when people closed their eyes. Just as expected, right? Stronger alpha oscillations. But the traditional alpha power measures, all over the map. Sometimes they went up, sometimes they barely changed, sometimes they even decreased. And crucially, there was very little correlation between the traditional alpha power and this new EA measure.
Wow. So it's like getting two totally different readings for the same basic phenomenon.
Yeah.
That really underscores the potential problem with the old methods.
It really does. That stark difference shows how misleading the traditional metrics can sometimes be. Easier, or EIA, seems to provide a much more precise, much more sensitive measure of the actual periodicity, the real rhythm. It's almost like a signal-to-noise ratio specifically tuned for the brain's internal rhythms. And another bonus, it's also significantly less bothered by those eye blink artifacts contaminating the alpha band. Why? Because it focuses on finding local differences in the power spectra, those sharp periodical peaks, rather than trying to fit a smooth curve to the entire noisy signal, background hum and all. So you get a much cleaner, arguably more accurate picture of what the brain's really doing rhythmically.
Okay, so we've got these incredible simulators now. They help us learn, they help us test algorithms, they even let us build these digital doppelgangers of brain states. And now we also have these smarter ways, like IA, to analyze the real signals hidden within all the noise. So looking ahead, what's next? What does the future hold for designing these digital brains and using them to better understand our actual organic ones?
Well, the advanced EEG signal simulator itself has a roadmap. They're planning to add more complex waveforms, like gamma waves, which are linked to higher-level cognitive stuff. And continuing our little theme of irony here, they're planning to add even more types of artifacts. Things like EKG, the electrical signal from the heartbeat, which can definitely show up on scalp EEG. And even that infamous 50 or 60 hertz power line noise, the static hum from your electrical outlets finding its way into your brain data. It comes back to that idea. To make a simulator truly useful, it needs to be almost as messy and inconvenient as reality itself.
More noise. You weren't kidding. So the quest for the perfect synthetic data actually means making it as realistically flawed as possible. It's this beautifully perverse cycle, isn't it? Build something perfectly clean, then meticulously add all the real-world imperfections back in.
Exactly. And it's not just this one tool either. There are other simulators emerging, often open source, like Unfold SimJL, These are offering even more complex simulations, things like multi-channel support simulating data from many electrodes at once, and even more realistic types of noise. And look, these aren't just academic toys for people to play with, they're becoming essential, critical tools. They let researchers rigorously test and validate the algorithms that could, one day power really advanced brain-computer interfaces. Think communication for locked-in patients or controlling prosthetics. Or they could lead to much better diagnostic tools for conditions like epilepsy or maybe even Alzheimer's disease. These simulators help accelerate that kind of discovery.
And for people who want to dive into real brain data, warts and all, even with all its glorious chaos, there are resources out there too, right? Like open data repositories.
Oh, absolutely. There are some fantastic open source repositories now. Places like the OpenBCI community website, OpenNeuro is a big one, the NMT Scalp EEG dataset. These platforms host huge amounts of real human EEG data that researchers, students, or even just curious individuals can access and analyze. So yeah, the brain in all its messy, complex, rhythmic glory, it's becoming more accessible for study than ever before, both in its raw biological form and through these increasingly sophisticated digital copies.
So we've taken quite the journey today, a deep dive into this surprisingly complex world of simulating brain waves and analyzing the signals. From creating these perfectly clean digital brain states to then painstakingly recreating all the biological noise that makes reality so tricky, it seems pretty clear that understanding the fake really does help us understand the real. It's been critical, definitely fun, and yeah, profoundly ironic too.
Absolutely. And maybe if we connect this back out to the bigger picture, it raises a really interesting question for you, the listener, to think about. How does this constant dance, this back and forth between creating controlled, perfect simulations on one hand, and then deliberately grappling with messy, noisy reality on the other? How does that change how we should approach any complex biological system? When we build these incredibly precise digital copies, what important details, what vital nuances might we risk overlooking in the real thing? And conversely, what unexpected truths, what critical insights do we perhaps only stumble upon when we fully embrace the imperfections, the noise, and the beautiful chaos of reality itself?
Yeah, okay, there's a human in the loop. If you have any questions, go for it. Let's do a quick music break and we'll go from there. Okay, we're not having much luck with the music today. Let's jump to the next review. We'll just comment along as well. We do Notebook LM in beta interactive mode. See how that goes.
Welcome back to the deep dive. Today we're plunging into something huge. Psychiatric disorders. I mean, the burden is staggering, immense distress, people unable to function. And it costs the world, what, $5 trillion US? It's mind-boggling.
It really is. And the core frustration, the thing that makes it almost cruel, is the lack of clear, objective ways to diagnose and treat these conditions.
Exactly. You've got this global crisis of the mind, and we're often relying on, well, subjective reports.
Right. The current symptom-based diagnosis, what a patient tells you, it often means treatment gets delayed, or maybe it's not quite the right fit for that person.
Which is why everyone's hunting for biomarkers, isn't it? These objective signs.
Precisely. We desperately need something concrete, measurable, that actually reflects what's happening inside the brain.
So, okay, when we talk about looking inside the brain for these markers, what's the main technology everyone gets excited about? What's its initial appeal?
That would definitely be electroencephalography, EEG. Basically, it's a recording from the scalp, captures the brain's electrical buzz.
The buzz, I like that.
Yeah, it's the sum total of all these tiny electrical potentials from millions of neurons firing, or rather, their postsynaptic potentials. It's like listening to the brain's orchestra from outside the concert hall. Not the individual instruments, but the overall sound.
Listening from the outside. Got it. And the appeal is, well, pretty obvious, right? The sources really hammer this home.
Oh, absolutely. Key advantages, it's non-invasive, no needles, nothing scary.
Huge plex.
It's way cheaper than, say, an MRI. Much more accessible.
Right.
And you get real-time data. It has fantastic temporal resolution, meaning it catches those super fast changes in brain activity, millisecond by millisecond, things slower methods would just completely miss.
So zooming out again, why is finding these biomarkers so absolutely critical for psychiatry? You mentioned the subjective diagnoses.
Well, yeah, the current system, like using the DSM, the Diagnostic and Statistical Manual, it leans so heavily on interviews, on observed symptoms, and that can lead to diagnostic instability.
Meaning the diagnosis can change.
Exactly. Symptoms shift, new ones pop up. It can be a bit of a diagnostic Wild West, honestly, which makes getting the right treatment and getting it quickly really tough.
Definitely paints a picture of the challenge. And that's where EEG comes in with all its promise, looking for those specific characteristics.
Researchers have looked at a whole host of things. For depression, there's been a lot of talk about alpha asymmetry. That's an imbalance in alpha waves between the left and right sides of the brain.
That one's been a bit controversial, though, hasn't it?
It has, yeah. Not always consistent, but they've also looked at increased gamma band power, linked to higher cognitive stuff, and changes in REM sleep, like more REM sleep, but starting sooner. Even things like higher EEG complexity, maybe suggesting the brain's struggling to regulate itself.
Okay. And what about bipolar disorder?
There, the focus has often been on abnormalities in alpha activity too, especially in frontocental areas. Seems linked to cognitive issues. And what's really interesting is how some brainwave patterns, beta, delta, theta, might actually normalize when someone responds well to lithium treatment.
Ah, so potentially a way to track treatment.
That's the hope. Could be a way to monitor if it's working. Plus, things like increased beta activity during manic episodes might signal that neural excitation.
And schizophrenia, that seems even more complex.
It is. Sources mention increased delta and theta power but less alpha power, suggests baseline disruptions. But maybe even more revealing is the work on event-related potentials, or ERPs.
ERPs, right? Those tiny signals in response to specific events.
Exactly. Things like P50 sensory gating deficits. Basically, the brain can't filter out irrelevant noise, leading to that feeling of being overwhelmed.
I see.
Or N100 amplitude reduction, suggesting issues processing sounds initially. And the P300 component that reflects attention, memory, decision-making, that's often different too.
These all sound like really hopeful early insights, right? Getting a real glimpse under the hood.
They definitely offer objective windows into what might be going wrong in these incredibly complex conditions.
So if we found a truly reliable EEG biomarker, What's the big aha moment we're hoping for? How would it change things for a patient versus today's system?
The are not moment, the real game changer, would be getting to truly personalized medicine in psychiatry. Imagine a quick EEG helping a doctor diagnose depression or bipolar much earlier, maybe telling similar conditions apart,
Okay.
or even predicting which medication or therapy might actually work best for you for that specific individual.
So less trial and error.
Way less trial and error, faster effective treatment, better outcomes, less suffering. It could really shift psychiatry from that diagnostic Wild West to something much more precise, much more data-driven.
That's a powerful vision. Okay, but here's where it gets really interesting and maybe a bit darkly funny. Despite all that promise, EEG biomarkers aren't really standard clinic tools yet for diagnosis. Why not?
Yeah, this is the reality check. There are some major hurdles. One big one is spatial resolution. It's just low.
Meaning,
Remember the orchestra analogy. Listening from outside the hall, you can hear the music, but pinpointing exactly which violin in which section. Very hard. EEG struggles to tell you precisely where in the brain activity is coming from, especially deeper down.
okay, so location is fuzzy. What else?
Then there's the noise problem, and this is where it gets almost comical. EEG signals are so easily messed up.
By what?
Oh, everything. External stuff like electrical interference from equipment nearby, sure, but also your own body.
My body.
Yeah, blinking your eyes, clenching your jaw slightly, tiny muscle movements in your scalp, even your heartbeat showing up in the signal. The skull and scalp themselves resist the electrical signals. It's like your body is actively trying to sabotage the recording.
Haha, okay, that is kind of darkly funny. Your own body is noise.
It makes getting a clean signal, especially for the really subtle brain patterns linked to psychiatric conditions, incredibly difficult. Those faint whispers are easily drowned out by biological static.
It sounds like a nightmare just trying to get usable data. How on earth do they manage that?
Oh, it's a constant battle. Technologists are incredibly vigilant. They meticulously prep the scalp. They watch the patient like a hawk for any movement. They use sophisticated algorithms to try and filter out heartbeat artifacts, eye blinks.
Wow.
It's this continuous detective work trying to isolate the real brain signal from all that physiological and environmental clutter.
And I guess interpreting that messy data isn't simple either. It's not just looking at squiggly lines.
Not at all. You need serious signal processing know-how, deep knowledge of neurophysiology, bioinformatics skills. You have to know what's signal, what's artifact, what's just noise.
Right. And you mentioned consistency earlier, or lack thereof.
Ah, yes, the standardization issue. Or maybe the non-standardization issue. It sometimes feels like a totally novel concept in parts of the field.
Meaning,
Different labs, different clinics, they might use different equipment, different procedures for recording the data, different software, different algorithms for analysis.
so everyone's speaking a slightly different language.
Kind of. It leads to results that are inconsistent. You can't easily compare study A to study B, and that really, really hinders progress towards something reliable enough for widespread clinical use.
That makes total sense. And layered on top of all that technical stuff is the nature of the disorders themselves, right?
Exactly. Psychiatric disorders are messy. Their heterogeneous depression looks different in different people. Symptoms overlap massively between disorders. People often have more than one condition, high comorbidity.
So unlike, say, Huntington's, where there's a clear genetic marker.
Right. There's rarely a single biological smoking gun for something like schizophrenia or major depression. The DSM symptom clusters, while useful clinically, actually make finding a clean, consistent biomarker even harder for researchers. Diagnostic instability can even mess up the research studies themselves.
Which I suppose brings us perfectly to maybe the most, let's say, illustrative example of the pitfalls, the split alpha incident.
Oh, yes, the split alpha scandal, a classic.
So some researchers announced they'd found this new phenomenon, right? Two or more peaks close together in the alpha frequency band. Sounded pretty groundbreaking.
Looked like they'd found maybe new brain generators working at slightly different alpha speeds. Very excited stuff. But the punchline, delivered quite bluntly in one of our sources, is that split alpha isn't physiological at all. It's not real.
Not real?
Nope, it's a completely spurious effect, a ghost in the machine, an artifact caused by messing up the math.
Lexing up the math club.
By using a standard tool, the fast Fourier transform, or FFT, on data segments that were too short. When you analyze a wave using too short a snapshot, you can get this thing called spectrum leakage.
Spectrum leakage.
Imagine trying to identify a musical note by hearing just a tiny fraction of a second of it. The analysis might mistakenly create echoes or phantom frequencies around the real note because the window was too small. That's basically what happened. These split peaks were illusions created by the analysis method, not by the brain.
Wow. So they found a glitch and called it a discovery. That's Quite something.
And it gets worse. They started assigning meaning to these phantom peaks, claiming they represented new generators in different parts of the brain.
Oh dear.
And then the real kicker, suggesting that where these supposed generators were located depended on which reference electrode they used for the recording.
Wait, isn't that like Electrophysiology 101? The reference is just a comparison point. It can't change where the signal comes from.
Exactly. It's a fundamental misunderstanding. It was, frankly, an embarrassing blunder, but a really instructive one.
Absolutely. It just hammers home that fancy tech isn't enough. You need rigorous methodology, which ironically brings us to the other side of EG, the clinical side, where they live by these incredibly strict rules.
It highlights the unsung heroes, the EEG technologists, and their rulebook, these minimum standards.
And the standards themselves sound intense. One source quotes the American Clinical Neurophysiology Society saying minimum standards provide barely adequate fulfillment of responsibilities to the patient. Barely adequate.
That tells you how high the stakes are, how precise you need to be.
And the details. Minimum 16 channels recording at once, specific electrode types like silver chloride, checking impedance, the electrical contact, making sure it's super low, ideally under 5K ohms.
Right, because even a little bit of bad contact acts like static, drowning out those faint brain signals we need. And using that precise 10-20 system map for placing all 21 electrodes, ensuring everyone measures from the same spots.
It's incredibly meticulous. And then there's filtering the signal. You mentioned that can cause problems too.
Oh yeah, filtering is essential to reduce noise, but it's another potential minefield. Pausal filters, the ones you can use live, can actually distort the timing, create ripples, shift when activity appears to happen.
So it looks like something happened later or earlier than it really did.
Potentially, yes. Zero-phase filters are better for preserving the signal's shape and timing because they process forwards and backwards, but you can only use them after the recording is done.
Okay.
So the technologist has to be constantly watching, spotting potential filter artifacts. Even the common 60 hertz knot filter for power line interference is used sparingly because it can mess with real brain activity near that frequency.
It's just layer upon layer of potential issues. And then they deliberately try to provoke brain activity, the choreography.
Standard procedures, simple stuff like opening and closing the eyes, watching how alpha waves change.
Okay.
But then it gets more intense, hyperventilation, having the patient breathe deep and fast for at least 3 minutes.
Why?
It changes brain chemistry slightly and can actually provoke seizures, which helps in diagnosis, both epileptic ones and sometimes psychogenic non-epileptic seizures too. Though obviously they don't do it if someone's had a recent stroke or is pregnant, safety first.
Still sounds pretty intense. What else?
Photic stimulation, flashing lights at different frequencies, another classic seizure provocation technique.
A party trick indeed.
And then there's sleep. The guidelines want a good chunk of sleep recording, maybe 30 minutes plus 20 minutes awake, often induced by partial sleep deprivation beforehand.
Which you mentioned there were no safety studies for.
Correct. One of those slightly dark, ironic footnotes in the guidelines. Or sometimes they use melatonin. It's quite an ordeal for the patient, all to get reliable data.
It really underscores the human element. The technologist isn't just hooking things up. They're managing the patient, noting every little thing, even testing responsiveness during a potential seizure.
Absolutely. Calmly asking, lift both arms up or repeat these words, horse, table, while someone might be having a seizure. It's incredibly skilled, high-stakes work.
So given all this complexity, all these challenges, where do we go from here? Is AI the savior?
Well, that's certainly the big hope. Artificial intelligence, deep learning. The promise is that these techniques could revolutionize EEG analysis. Handle the toys, the complexity, maybe spot subtle patterns humans miss, automate artifact rejection, analyze huge data sets.
Find those elusive biomarkers.
That's the goal. Overcome many of those traditional limitations.
There's always a but, isn't there?
Always. AI needs massive amounts of really good, well-characterized data to learn effectively. Huge data sets, meticulously cleaned and labeled. That's a challenge in itself. And then there's the interpretability problem. These AI models can be like black boxes. They might find a pattern, but can we understand why it's relevant?
So are we just trading one kind of messiness for another? Could AI just find new, fancier ways to generate split alpha artifacts only faster?
Haha, that's the cynical but not entirely unfair question. It's possible. AI is a powerful tool, absolutely. But the core need for scientific rigor, for critical thinking about the data and the methods, like the split alpha story showed us, that doesn't go away. If anything, it becomes even more important.
So bringing it all together then, what does this mean for you, our listener, trying to get your head around this? EEG clearly has huge potential. Non-invasive, fast, relatively cheap.
And it has given us real promising clues about the brain mechanisms in depression, bipolar, schizophrenia. It hints at that future of objective diagnosis and personalized treatment.
But that journey to the clinic is just riddled with obstacles. Technical complexity, noise, standardization issues, human challenges, and these really basic methodological traps like split alpha.
Right. It shows that cool tech isn't the whole story. The underlying science, the careful interpretation, that's crucial. Split alpha isn't just a funny anecdote, it's a really stark warning about how easily we can fool ourselves, especially when we're desperate for answers. Rigor matters. Understanding your tools matters.
So for you listening, understanding these challenges is key. It's a reminder that even in hard science, maybe especially in hard science, critical thinking about how we get our data is just as vital as the data itself. And it shows the reality of scientific progress. It's often messy, painstaking, rarely a straight line.
Especially when we're dealing with the brain, it's also that cautionary tale. Beware of new phenomena that might just be glitches in how you looked. Always question the methods.
Which leaves us with a final thought. In a world crying out for objective answers to very real subjective suffering, what does it truly mean when even our most sophisticated scientific tools require such intense scrutiny to tell a real insight from, well, a glorified glitch? Maybe the hardest part about understanding the brain isn't just its complexity, but our own struggle to read its signals without accidentally making things up along the way.
Okay, we have this Gemini made this simulator for us, so you know what's coming on BioniChaos.com. Yeah, well, I was having trouble fitting it into the screen. Yeah, so we have the kissing. Oops. So you have this signal, to be an EEG signal, so you can amplify. Ooh, something happened there. Okay, can amplify, high pass field. Okay. Is it even accurate? Notch filter. Yeah, anyway, you get the drift. It will be like a simulation game for filter design. There's a keyboard. Okay, that's nice. Keyboard left, right. Can adjust the noise. Yeah, well, you get the picture. I'll try to improve on something like that. Mouse touch, drag horizontally left, right across the canvas to decrease the amount of noise. That's okay. That's nice. But like, well, we like it working everywhere. So, okay, that's too loud, isn't it? We like it to work with your touchscreen, mouse, and keyboard as well, which it does, but yeah, needs more work. Needs more work. Okay, we did a deep research on stuff on EEG filtering. We got this website. So we have the interactive report. No, wait. You have the signal recording engineering precision and clinical expertise in EEG interpretation. Okay, it's having all the sources. Yeah, well, the point of it is that you can actually turn it into a web page. So we have the Mirage, the signal chain, patient electrode amplifier, ADC, it's analog to digital conversion, software, and the interpreter, which in most cases is a clinician. We don't have a clinician. So we're using AI just because it's too expensive to have access to a clinician. So we have cognitive biases. Yeah, it's really nice, really nice. Confirmation bias, anchoring bias, availability, heuristic, premature closure, accepting a diagnosis before it has been fully verified, ending inquiry too early. Yeah. Can only imagine how often does that happen. And yeah, we don't want to just talk about the problems. We have some solutions. So education, better standards, intelligent systems. So we'll be focusing on those for obvious reasons. Well, we are not in academia. We are not setting standards. So we are not powerful enough, but we can design simulations and train models. So there you go. So that's a nice little thing. From those reports, we have the report. We can download it as PDF. Obviously, we had things like that on the website already. Go check it out. You can create a web page, infographic, a quiz. A quiz will be nice. You can actually learn, test your comprehension. And what else can you do? What else can you do? We had a subscriber. Thank you very much. Don't forget to like and comment as well. Your interaction is very important to us. Okay, we keep diving into the EEG wormhole. EEG wormhole. Ooh, something. Oh, I thought something happened to Gemini. I thought we lost our CEO. No, we still have it. Still have a CEO. Yeah, just generating like infographics and content out of that very long report, which obviously no one will read, but yes, we can make it available as a can make it available as PDF. PDF. Okay, we can do a quiz, audio summary out of it. Yeah. So yeah, this video brought to you by Gemini. Funny how as soon as I start talking, like people don't like AI, but then as soon as I start talking, the views go down. That's unfortunate, isn't it? That's very unfortunate. Well, what would you do? Yeah, we do have traffic on the yeah, lots of traffic. Okay, let's do the next thing. Don't remember what the prompt was. Yeah, notebook LM is a bit interesting that way. Oh yeah, well yeah, because there's so many different ways of using it as well. Yeah, and also ask for 8 to 10 minute summary, but give me 15. So yeah, not sure. I'm not even sure if it's following prompts at all. I suspect it's not, but it is. It seemed to be true to the sources added in the conversation. So yeah, so we have a bunch. We'll do a summary. Just keep diving in. Go check the website. Let us know what you think. Actually might load this brain, because I might start losing frames as I do. So I load this tool. Do I lose frames? No, I didn't drop any frames. I didn't drop a single frame. Oop. Yeah, I can't minimize, so maximize the screen. Yeah, I can only do oh yeah, feeding stuff into the screen is a bit of a pain, isn't it?
Imagine trying to listen to the most intricate symphony, but you're stuck in a really crowded concert hall.
Right.
There's coughing, people shuffling, maybe a phone goes off. That's kind of what it's like trying to decipher the brain's electrical activity, isn't it?
That's a great analogy.
Yeah.
Yeah, it's definitely less serene string quartet, more like a full orchestra competing with a pretty unpredictable audience.
Totally. So today we're doing a deep dive into electroencephalography, EE for short.
Yeah.
Our mission, to shortcut your way to getting a handle on how these tiny brain signals are captured, what kind of noise messes them up, and believe me, some of that noise is weirdly personal, almost darkly funny.
Mm-hmm.
We'll look at the clever ways researchers try to clean it all up, and then the real kicker, why for some really advanced stuff that noise might actually be helpful.
Exactly. We've got a good stack of sources lined up to walk us through this whole intricate process.
Okay, let's unpack this then. We know EEG measures brain activity, but how precisely do we even pick up those super faint electrical signals from someone's head?
So at its core, EEG is a non-invasive way to measure the collective electrical buzz of huge groups of neurons firing together synchronously.
Okay.
Think of it like trying to hear the orchestra's overall sound from just outside the concert hall door.
Mm.
You're not disturbing the players inside.
And how do they physically capture that sound? You can't just stick electrodes anywhere, I assume.
Oh, definitely not. It's all about precision. The gold standard is something called the 10-20 system.
Okay, 10-20.
Yeah, imagine drawing really precise lines on your scalp. You use specific landmarks, like that little dip at the top of your nose.
Right between the eyes.
Exactly. And the inion, that bony lump at the back of your head.
Mm-hmm.
From those points, you place 21 electrodes symmetrically. They're measured at specific 10% and 20% intervals of the skull's perimeters.
Ah, hence the 10/20.
Precisely. And this standardization is absolutely crucial. It means recordings from different people, different labs, different times, they're actually comparable. That's vital for research, for diagnostics.
Okay, so we're all hooked up nice and neat. What are we actually hearing? Does the brain play different tunes depending on what it's doing?
That's a really good way to think about it, yeah. EEG doesn't just measure activity in general. It reveals these distinct electrical rhythms or waves that tell us what the brain is up to, both in time and across different areas.
Like different musical scores?
Sort of. For instance, if you're relaxed, maybe eyes closed, chilling out, you're likely producing rhythmic alpha waves. They're typically between 8 and 13 hertz.
So meditation mode equals alpha tune.
Pretty much. Now, if you're really focused, concentrating hard, or maybe even feeling a bit anxious,
Yeah.
we see faster beta waves. Those are anywhere from 14 up to 50 hertz.
Okay, faster for more active thinking.
Right, and then there are slower ones too. Theta waves, that's 4 to 7 hertz, often linked to mental stress, maybe drowsiness, and even slower delta waves, 3 to 5 hertz, which really dominate when you're in deep sleep.
Makes sense. Deep sleep, slowest rhythm.
Exactly. And then way up at the fast end, you've got gamma waves. We're talking 40 to 140 hertz.
Wow.
Yeah, those are associated with peak focus, intense thinking, maybe even consciousness itself. It's this incredibly complex mix, millions of neurons firing, synaptic currents, even the physical shape of your head plays a role.
But the brain isn't the only thing making electrical noise up there, is it? And this is where it gets, well, kind of funny in a dark way. The noise can be very personal.
Oh, absolutely.
Yeah.
An artifact in EEG is just any electrical signal that doesn't come from the brain itself.
Okay.
It's all that extra chatter in our concert hall. We usually split them into two main types. Physiological, coming from your body, and non-physiological, from outside sources.
Physiological. So interference literally generated by us, our own biology getting in the way.
You got it.
Yeah.
Your normal bodily functions can create huge interference. Think about simple things. Moving your eyes, blinking.
Just blinking, really?
Oh, yeah. Even chewing or grinding your teeth, that's called bruxism, or just swallowing. These muscle contractions, they generate electrical signals way, way stronger than the brain's own signals.
No way.
Seriously. One source we looked at showed how a single swallow lights up almost all the electrodes with these huge spikes.
Huh. So your brain's trying to compose this masterpiece, and your jaw deciding to chew is like a sudden, deafening drum solo.
Small chuckle. That's pretty much it. And it's not just muscles. Your heartbeat, the EKG signal, even just breathing, sweat glands.
Sweat glands.
Yep, skin potential changes. Or if someone has an artificial pacemaker, that's another source of electrical noise. It really is kind of darkly humorous that just being alive makes it harder to listen to your brain.
Especially someone's stressed, right? They probably move more.
Exactly. Anxiety, stress, finding it hard to stay perfectly still, that often makes these physiological artifacts worse.
And then there's everything else, the whole world trying to butt in.
Precisely. That's the non-physiological stuff.
Yeah.
It can be mundane things like a bad connection where the electrode meets the scalp, maybe it's placed wrong, or faulty wiring.
It's technical glitches.
Right. But it also includes electromagnetic fields just floating around in the environment. The hum from the power grid, 50 hertz here, 60 hertz in the US.
The mains hum.
Yeah. Other medical equipment, if you're in a hospital, your cell phone, even fluorescent lights, all that can interfere. Sometimes you see what's called an electrode pop.
A pop.
Yeah, it's like this abrupt, spiky jump in the signal when an electrode just momentarily loses good contact. It really underscores there's a constant battle researchers fight just to get a clean recording.
Okay, so with all this, unwanted input, crashing the party, the huge challenges, how do you filter out all these uninvited guests without accidentally throwing away the important brain signals you actually want?
That is the million-dollar question. It's this incredibly delicate balancing act. Whatever cleaning method you use, it's crucial. It doesn't create new problems, new artifacts, or just erase valuable neurological data.
So what are some of the, let's say, classic ways people have tried to tidy up this messy signal?
Well, historically, the methods range from pretty simple to really quite complex. If you're looking just at the signal over time, you might do basic amplitude thresholding.
Meaning?
Like if the signal suddenly jumps to 6 times its recent average height within, say, 10 seconds, you flag it.
Yeah.
Probably an artifact, right? Too big, too sudden.
Okay, like a that doesn't look right filter.
Kind of. Or you can get more subtle using mathematical models. There's one called a quadratic linear parabolic model. Its parameters, how they change, can help distinguish the shape of a normal resting signal from, say, a muscle twitch artifact.
So looking at the shape of the wave, not just how tall it is.
Exactly. Then moving into the frequency domain, looking at the different rhythms, there are techniques like musicus, multiple signal classification.
Music. Okay.
Yeah, it cleverly works by estimating the frequency profile of the noise itself, so you can then subtract it out. It's pretty effective, but it takes a lot of computing power.
Resource intensive.
Very. Another approach is the empirical wavelet transform. This one's cool. It adapts its filters to the signal itself, almost treating the EEG data like an image, finding patterns.
Turning brainwaves into pictures again? That's neat. A smart way to zero in.
It really is. And beyond just time or frequency, statistical modeling is huge too. Like you can try fitting the EEG data to a specific statistical distribution, a T-location scale distribution, for example.
How does that help?
Well, the specific parameters of that fitted distribution, its shape, its spread, they can act like a fingerprint. Different artifacts like teeth grinding or a cell phone buzz might distort the distribution in characteristic ways compared to normal brain activity.
Okay, so using stats to spot the odd ones out.
Oh.
Clever.
So we're trying all these ways to pick out the brain's true voice from all the surrounding noise. And I think you mentioned some of the really heavy lifting involves multivariate analysis. What's going on there?
Yeah, what's that about? Sounds complex.
It means we stop looking at each electrode signal in isolation. Instead, we look at the relationships between all of them, or many of them, at the same time. Consider the whole set of measurements together.
Okay.
A really popular approach here is blind source separation, or BSS. The basic idea is to try and unmix the recorded signals, assuming they came from different independent sources that all got jumbled together at the electrodes.
Like trying to separate out individual instruments from a bad recording where everything got mixed onto one track.
That's a perfect analogy. Principal component analysis, PCA, is a classic BSS method. It finds the main directions of variation in the data, trying to boil it down to the most important underlying patterns.
Sounds useful.
It can be, but honestly, it's not a magic bullet. PCA often struggles to cleanly separate things like eye movements or muscle activity or even the heartbeat signal, especially if those signals are roughly as strong as the brain signals you're after.
Right.
That's like trying to untangle spaghetti. But some strands look almost identical to others, and they're all kind of sticky.
Frustrating. That almost but not quite feeling.
It really can be. Which naturally leads to the question, if PCA isn't quite cutting it, what's next? And that's often independent component analysis, or ICA.
ICA. How's that different?
Well, ICA takes a crucial extra step. It specifically tries to transform the data not just into uncorrelated components like PCA, but into statistically independent components.
Independent.
Meaning the sources are assumed to be generated by distinct processes that don't influence each other. Think of eye blinks and alpha waves. They come from different biological generators.
Yeah.
ICA is designed to exploit that independence to unmix them more effectively.
Oh, okay. It leverages the idea that these signals should be separate.
Exactly. And many studies show it works quite well for removing common artifacts. Interestingly, there's a little trick. Applying a high-pass filter before running ICA can sometimes boost its performance for certain analyses.
That pre-filter helps.
Sometimes. But there's always a trade-off, right? Doing that can negatively affect something called dipolarity.
Dipolarity.
Yeah, it's basically a measure of how well the separated component resembles a signal coming from a plausible single-point source within the brain. So you might get cleaner separation with the filter, but the resulting brain components might look less biologically realistic. It's that classic engineering compromise.
Fascinating. Okay, so that brings us towards the cutting edge. How are the latest computational tricks, AI, machine learning, tackling this never-ending cleanup job?
Yeah, we're seeing some really exciting new things emerge. For instance, there's a new metric called oscillation energy, or E sub alpha.
alpha.
Right. Its goal is to characterize genuine brain oscillations much more precisely. See, traditional methods often look at broad frequency bands, right, like 813 hertz for alpha. But that often lumps together the real oscillation peak with just general background noise or non-rhythmic activity in that band. EJA tries to specifically amplify and separate out the peak of the oscillation from that background mush.
So it's like really fine-tuning the receiver to get just the core melody, not the static around it.
That's a great way to put it. It makes it much more sensitive to subtle changes in brain activity and less swayed by just general background shifts.
That sounds like a big step for understanding specific brain functions.
It potentially is. And then, of course, there's the huge wave of artificial intelligence and deep learning. These tools are just fundamentally changing how we analyze EEG. We're moving way beyond staring at squiggly lines on a screen.
How so?
Well, for example, people are tuning large language models, like the ones behind chatbots, but feeding them vast amounts of neuroscience knowledge.
Wow.
Yeah, to help with diagnosing diseases from EEG data, even generating explanations that sound like a human expert's reasoning. It's pushing the boundaries, turning that raw signal into potentially actionable clinical insights.
Here it comes, right? The kicker, the aha
Yeah.
moment that flicks things around, especially for deep learning. It's got this wonderfully ironic twist.
It really does. Okay, so when you're preparing EEG data to feed into these powerful deep learning models, the standard thinking, the conventional wisdom has always been more pre-processing is better.
Clean it up as much as possible.
Exactly. Cleaner data, purer brain signal. Presumably the AI will learn better, perform better. Makes intuitive sense.
Yeah, totally. Garbage in, garbage out kind of thing.
But recent research, some really critical studies, have found something genuinely surprising. First off, feeding totally raw EEG data, like straight off the scalp with zero cleaning,
Yeah.
that generally leads to pretty poor results.
Okay, so raw's bad. That fits.
It consistently ranks last in accuracy tests.
Yeah.
But here's the turn. It turns out that often minimal filtering, maybe just basic stuff like removing the mains hum, often hits the sweet spot. It gives the best balance between how much work you put into cleaning and how accurate the model ends up being.
So not too much, not too little, the Goldilocks zone of data cleaning. But wait, there's more, isn't there? The ironic part.
This is it. The really sophisticated pre-processing pipelines, the ones using those established automated artifact removal methods like ICA that we talked about, the ones designed to give you the purest signal. They don't always help the deep learning models. In fact, sometimes these advanced cleaning steps are actually detrimental. They make the AI perform worse.
Wait, what? You're telling me all that hard work, carefully scrubbing the data, getting rid of the noise, might actually hurt the AI's ability to learn?
Yeah.
That is brilliantly, critically ironic.
It is, isn't it? And the implication is pretty profound. There's this growing suggestion that the EEG artifacts themselves, the eye blinks, the muscle twitches, maybe even other stuff.
The stuff we called noise.
Exactly. That stuff might contain subtle hidden information. Information that these deep neural networks, which are amazing at finding complex, non-obvious patterns, can somehow pick up on and use.
So the noise isn't just noise.
It seems maybe not, at least not to the AI. It's like the artifacts are whispering secrets that contribute to the model's overall performance. Secrets that our human-designed filters, aiming for purity, are just silencing. It really makes you question what clean data even means in this context.
Wow. Okay, so what does this all mean for you, the listener, trying to get your head around these complex brain signals and how scientists study them?
Well, I think it means that understanding EEG isn't just about recording the brain. It's also about critically understanding what isn't the brain, the interference, and then making really informed, sometimes quite counterintuitive choices about how you deal with that interference.
Right. The best approach isn't always the one that seems cleanest on the surface.
Exactly. This deep dive really throws up a fascinating paradox, doesn't it? Our intense search for perfectly clean data might, in these advanced AI contexts, actually lead us to throw out valuable information hidden in the mess.
It definitely challenges our assumptions about data purity versus actual utility, especially as AI gets better at finding patterns we just can't see ourselves.
It's a powerful reminder, I think. Sometimes the perfection we aim for can blind us to unexpected value in what we initially dismissed as just noise.
Which leaves us with a provocative thought, doesn't it? What other noise in our lives, in all the data swirling around us every day, might we be filtering out too quickly? What hidden information might be lurking in the stuff we usually discard, just waiting for something or someone sophisticated enough to actually hear it?
Just imagine for a moment a world where we could genuinely peer into the brain's electrical symphony.
Yeah, like really understand what's happening in there.
Exactly. Using something like electroencephalography, EEG,
Yeah.
to maybe finally unlock the mysteries of really tough conditions like depression or bipolar disorder or schizophrenia.
Oh, absolutely. The potential seems enormous, especially when you think about looking for those specific patterns, those biomarkers.
Right. Things like the P300 wave may be tied to attention or alpha rhythms for relaxation states. The promise for, well, for diagnosis, for treatment. It feels revolutionary.
It really does.
But, okay, here's the twist. What if some of those really eye-popping claims we hear about brain decoding, like telling emotions just from brain waves or even making images appear from thoughts?
Yeah, the super advanced stuff that gets all the headlines.
Exactly. What if it wasn't quite solid? What if, in some of these supposedly groundbreaking studies, the brain they were reading? Well, what if it wasn't actually a brain at all?
Yeah, now you're touching on a really fundamental challenge in the field. It sounds technical, but it's crucial. Temporal autocorrelation.
Could break that down. Temporal autocorrelation.
Yeah, basically it just means the electrical signal you record at one specific moment is often really similar, highly correlated with the signal just a fraction of a second before or after it.
Like an echo, almost.
Right.
Or a hum.
Kind of like a persistent hum, yeah. Think of your fridge humming. It's consistent, right? This natural consistency in EEG signals can create this illusion of a meaningful pattern.
So the system thinks it's seeing something complex.
Exactly, when maybe it's just picking up on that same old background hum, that static repeating itself.
Okay, so this sounds like where our deep dive is headed today. A scientific revelation that's maybe a little bit funny, a bit weird,
Definitely weird.
but really important for anyone looking at AI, brain science, all that. And it involves an unlikely cast, right? A neural network, a lab, and watermelons.
Yes, watermelon.
Right, so this is where it gets, frankly, fascinating. Researchers needed a way to isolate this temporal autocorrelation problem. How do you get EEG data without any real brain activity happening? No thoughts, no reactions to stimuli.
Their solution was, well, ingenious and maybe a touch dark-humored.
Which was?
Record EEG from watermelons.
Actual watermelons wearing the little electrode caps.
Yes. Electrode caps sitting patiently in the lab like tiny, green, completely non-sentient subjects. And they were thorough. They created what they actually called the watermelon EEG dataset. 10 different watermelons, each wired up, recording for over an hour.
An hour of watermelon thoughts.
Or rather,
non-thoughts.
Precisely. No neural responses, nothing to interpret in terms of brain function, just the raw, inherent electrical noise or hum of a piece of fruit.
So what happened when they fed this data to a neural network?
Well, this is the kicker. A pretty standard, simple neural network could achieve incredibly high decoding accuracy using this watermelon data.
Wait, decoding what from a watermelon?
That's the point. It was successfully assigning labels, decoding them, but not because the watermelons were, contemplating existence.
Right.
It was because the continuous data stream from one specific watermelon had its own consistent, predictable electrical signature, its own domain feature, thanks to that temporal autocorrelation.
Ah, so each watermelon had its own electrical fingerprint, its own hum.
Exactly, a unique hum.
So the model wasn't learning about watermelon consciousness, obviously. It was just learning to tell the watermelons apart based on their background noise.
Precisely. It learned to classify the watermelon itself by its persistent electrical vibe, not any information it was processing. It learned the domain, the source, not the content.
It's like teaching a system to recognize different singers, but only ever giving it recordings of each singer humming the same note in a different room.
That's a great analogy. It gets really good at recognizing the room's acoustics for that hum.
But it can't actually identify the singer or a different song if you change the context.
Exactly. It learned the room, not the voice.
Okay, so this watermelon story, while amusing, points to a serious issue in actual human brain research, right? This idea of overestimated decoding accuracy. How does the way experiments are set up contribute?
Hugely. It often comes down to experimental design, especially something called block design paradigms.
Block design?
Yeah. Imagine you show someone, say, lots of pictures of faces, one after another, in a block. Then maybe a block of pictures of houses.
Okay.
The EEG signals recorded during the face block become very similar over time just because they're recorded close together. They get temporally correlated.
Ah, because it's one continuous stream while looking at similar things.
Right. And the model, well, it learns these block-related features, this domain signature of the face block, instead of the tiny specific brain responses to each individual face.
So it's learning the block, not the face.
Pretty much. It's taking the easy route.
And there's actual proof this happens in real studies.
Oh, definitely. There was one study using that kind of block design, and they reported like over 95% accuracy in decoding image types. Sounds amazing, right?
Incredible, yeah.
But then they reran it using a different setup, a rapid event design, where they mixed up the image types randomly, showing a face, then a house, then a tool, all jumbled.
So no more blocks.
No more blocks, and guess what happened to the accuracy?
It dropped.
Plummeted, down to basically chance level, like guessing, around 2.5%.
Wow, okay, so that's stark evidence. The high accuracy was an illusion built on that temporal correlation.
It really was. And this highlights something else just as critical, how you split up your data for training and testing the AI.
Data splitting strategy.
Yeah. If you train your model on data from one part of a recording block and then test it on data from another part of the same block,
Even if you shuffle it.
the model can still pick up on that underlying shared hum, that domain feature,
Yeah.
because it's present throughout the whole block.
So it looks like it's generalizing, but it's really just recognizing the same recording session's noise signature.
Exactly. The fix is something called a leave domains out strategy. You make absolutely sure your training data and your test data come from completely separate domains, different blocks, maybe different sessions, definitely not overlapping in time in a way that shares that autocorrelation fingerprint.
And when researchers do that properly,
Often the decoding accuracy drops, sometimes dramatically, even down to chance level, and this is with real human EEG data. It strongly suggests that a lot of models might be overfitting to these domain features, not truly understanding the neural response itself.
it's like that facial recognition system. Again, train it only on photos from one studio. It fails spectacularly out in the real world.
It's the same principle, and crucially, this isn't just about quirky experiments or bad setups. These temporal autocorrelations are inherent in our brains.
They're naturally there.
Yes, they're often called long-range temporal correlations, or LRTCs. They exist naturally in human EEG signals across all the different frequency bands we look at. Delta, theta, alpha, beta, gamma. It's just part of how the brain's background electrical activity works.
So you can't just easily filter them out.
Well, people try. They try filtering baseline drift or specific frequency bands, but it doesn't fully solve it because these LRTCs often overlap in frequency with the real brain signals you do want to measure. It's a fundamental challenge. Separating the genuine neural response, the brain reacting to something specific, from its own continuous background electrical hum.
So that really makes you pause, doesn't it? When we see these amazing headlines about AI decoding thoughts or intentions using EEG, how much is real decoding?
And how much is the AI just getting incredibly good at recognizing the unique electrical signature of that specific recording, or even that specific person's baseline brain hum, without truly understanding the content of their thoughts?
It casts a bit of a shadow, maybe. But,
Yeah.
okay, let's pivot slightly. Despite these pitfalls we've uncovered with some AI applications, EEG itself is still a cornerstone in clinical settings, right?
Yeah.
It's incredibly valuable.
Oh, absolutely essential. Indispensable, really.
So what makes that traditional clinical EEG, interpreted by humans, still so reliable despite these signal challenges?
It comes down to really stringent technical standards and critically careful expert human interpretation. A proper clinical EEG isn't just slapping on electrodes.
Right.
It involves meticulous protocols, precise placement, usually using a standard system like the 1020 International System to ensure everyone's recording from the same relative spots.
Consistency.
Exactly. And maintaining very low electrode impedance, that's the connection quality between the electrode and the scalp. You need a clean signal, minimal external noise, plus specific sampling rates to capture the brainwave details properly.
And then there's the noise problem.
Yeah.
Artifacts, you call them.
Yes, a huge part of the expert's job is spotting artifacts. Electrical noise that isn't brain activity. Muscle tension is a big one. It often looks really sharp, spiky on the EEG. Nothing like smooth brain waves. Like if you saw a spike that looked like you could sit on it and it would hurt, it's probably muscle.
Huh. Okay, a practical tip there.
Yeah. Eye blinks. Even the heart's EKG signal can show up. A trained eye learns to spot these and mentally filter them out or note them. We also sometimes use activation procedures.
Like flashing lights.
Exactly. Intermittent photic stimulation or having the patient hyperventilate. These can sometimes provoke abnormalities, especially in epilepsy cases, that you wouldn't see on a resting EEG. But you also have to be careful with those, know the contraindications.
And you need enough data, right?
Mhm.
Not just a few seconds.
Absolutely. A routine EEG is typically at least 20 minutes, maybe 30, if you're hoping to catch sleep patterns. Which is another thing sometimes we induce sleep, especially in kids, using things like sleep deprivation or melatonin, because certain abnormalities only show up during sleep.
So it's a really controlled, thorough process.
Very.
And it sounds like even with all the tech, the human expert, the neurophysiologist, is still key.
Absolutely irreplaceable, I'd say. They're the ones connecting the dots, seeing the patterns, yes, but also recognizing the noise, understanding the patient's clinical picture. It's this complex dance between the technology capturing the signals and the human expertise interpreting them correctly.
Okay, so we've really gone on a journey here today. Started with the amazing promise of AI reading minds.
Yeah.
Detoured through a patch of watermelons
The stars of the show.
and landed back at the maybe less glamorous but fundamental importance of just good, solid scientific rigor.
Meticulousness, yeah.
The power of AI is undeniable, sure. But this whole deep dive really hammers home that the data going in, how it's collected, how it's handled, how it's split, that matters maybe more than the fanciest algorithm.
It truly does. It's a critical lesson, I think. In this age of powerful AI, data quality and experimental design aren't just, boring technical details. They're potentially the difference between a real breakthrough.
And just fooling ourselves, maybe. Sophisticated self-deception, as you put it earlier. It's a good reminder, isn't it? Even when the machines are doing the learning, we humans still need to be asking the tough questions. The sometimes uncomfortable, maybe even slightly absurd questions.
Definitely need to keep asking.
Well, until next time, keep digging beneath the surface, because as we found today, sometimes the most surprising and important truths are lurking in really unexpected places.
Indeed.
So here's something to chew on. If AI can be trained to seemingly decode the non-existent thoughts of a watermelon, what other non-cerebral secrets might it be accidentally uncovering when it claims to understand us? And maybe more chillingly, how often do we mistake the hum of the system itself for profound meaning?